Let's take a look at some of the risk associated with some of our hypothesis testing. We talk a lot about the alpha risk. What's the risk that we'll basically make the wrong decision in our experiment? So if we look at the alpha distribution, the risk we take with our alpha, we typically have some mu that we're concentrating on that we think is the target mu. And in experimenting on that, we typically build ourselves in some buffer to allow for that. So we call that the alpha risk. Typically we draw some point. I'm going to draw this as alpha equals 0.01. So with a 0.01 alpha, we're saying that we can handle a 1% risk that we will accept the null hypothesis even if it's wrong. That doesn't mean that there's a 1% chance that this particular mu is wrong. It means that if we take 100 samples, 1 in 100 could be wrong. This could be that one. So we know that there's some risk here. This might not be the true mu for this population, but we have a certain element of risk there. So what we're typically managing is the alpha risk that goes on. There's a small chance in this case that we'll end up with the wrong mu and not know it as we go through. So typically what we do is we go out and find the real data. As statisticians, we don't know that data, but let's assume for the moment that the true data is very much like the sample that we took, that there's actually a true mu1 that is vanishingly small. It's not the same as mu sub 0, but it is different. So in essence, we should be rejecting the null hypothesis, but we're not, because it doesn't fall outside our threshold. So it isn't one of those 100 that we get. So if we extend down this alpha risk, we know that if the mu had been different enough, if the true mu is outside of the alpha risk, we'll still pick it up okay. But the problem is that where mu actually is, we're not going to pick it up. There's some beta risk involved. And that would have been true if the mu had fallen anywhere on this curve outside of our alpha risk. So we know we have beta risk that takes place across this entire curve. Now, this isn't drawn to scale, but in essence, if the difference in the mu's is vanishingly small, the beta is going to be about 0.99. It can't be exactly that, because if it were equal, we would have been outside the alpha risk and we would have rejected the hypothesis. So it's actually just a tad smaller than that, because basically our alpha plus our beta will always be less than but not equal to 1 as we go through. So that's the key as we go through, is those two risks go together. So if we look at our risk in this way, we can use these different curves. So typically if we take 1 minus our beta risk, we're talking about the power of our experiment, which again, if it's vanishingly small, is roughly equal to alpha. But as you'll see, as we extrapolate and look at different data points, it won't stay there and it won't be the same.